Lesson: Supervised Learning, Applications in Malware Classification. Supervised learning is a cornerstone of machine learning that has found significant applications in various domains, including malware classification. By leveraging labeled datasets, supervised learning models can be trained to identify and classify malware with high accuracy. This process involves mapping input features to the corresponding output labels, which is particularly useful in threat detection and cybersecurity. The ability to classify malware accurately is critical for preventing cyber attacks and ensuring the security of information systems. The following lesson delves into the practical aspects of applying supervised learning techniques to malware classification, providing actionable insights and guidance on using relevant tools and frameworks. In the realm of malware classification, supervised learning models are trained on datasets comprising features extracted from software samples, labeled as either benign or malicious. The objective is to develop a model that can generalize from the training data and accurately classify new, unseen samples. This is achieved by selecting appropriate features that effectively capture the distinctions between benign and malicious software. Common features include API calls, file permissions, and network behavior, which are extracted using static or dynamic analysis techniques. Static analysis involves examining the code without executing it, while dynamic analysis involves monitoring the behavior of the software during execution. The choice of supervised learning algorithm plays a crucial role in the effectiveness of malware classification. Popular algorithms include decision trees, random forests, support vector machines, and neural networks. Each algorithm has its strengths and weaknesses, and the selection depends on the specific requirements of the task. Decision trees, for example, provide interpretability and are easy to visualize, making them suitable for scenarios where understanding the decision-making process is important. Random forests, an ensemble of decision trees, offer improved accuracy and robustness by mitigating the risk of overfitting. SVMs, known for their ability to handle high-dimensional data, are effective for binary classification tasks, such as distinguishing between benign and malicious samples. Neural networks, particularly deep learning models, have gained prominence due to their capacity to learn complex patterns from large datasets, although they require substantial computational resources and data for training. To implement supervised learning for malware classification effectively, professionals can utilize a variety of tools and frameworks. Python, a versatile programming language, is widely used in this domain due to its extensive library support and ease of use. Libraries such as scikit-learn, TensorFlow, and PyTorch offer comprehensive functionalities for building and deploying machine learning models. Scikit-learn is particularly useful for classical machine learning algorithms, providing a range of tools for data preprocessing, model selection, and evaluation. TensorFlow and PyTorch, on the other hand, are well suited for deep learning applications, offering flexibility and scalability for training complex neural networks. A practical implementation of malware classification using supervised learning involves several key steps. The first step is data collection, where professionals gather a diverse dataset of software samples labeled as benign or malicious. This dataset serves as the foundation for training and evaluating the model. Next, feature extraction is performed to transform the raw data into a structured format that can be fed into the machine learning algorithm. Feature engineering, which involves selecting and transforming features to enhance model performance, is a critical component of this process. Once the data is prepared, the model selection phase begins. Professionals must choose an appropriate supervised learning algorithm based on the characteristics of the dataset and the classification task. After selecting the algorithm, the model is trained on the training dataset, adjusting its parameters to minimize classification error. During training, techniques such as cross-validation are employed to ensure the model's generalization capability and to prevent overfitting. Model evaluation is the next step, where the trained model is tested on a separate validation dataset to assess its accuracy, precision, recall, and F1 score. These metrics provide insights into the model's performance and help identify areas for improvement. If the model does not meet the desired performance criteria, professionals may iteratively refine the feature set, adjust the model parameters, or explore alternative algorithms. To illustrate the application of supervised learning in malware classification, consider the case study of a cybersecurity firm tasked with detecting ransomware threats. By employing a random forest classifier, the firm was able to achieve a classification accuracy of 95% on a dataset of ransomware and benign samples. The model's high accuracy was attributed to the careful selection of features, including file entropy, API call frequency, and network traffic patterns. This example demonstrates the effectiveness of random forests in handling complex, high-dimensional data and their ability to provide reliable threat detection. Despite the success of supervised learning models in malware classification, several challenges persist. One major challenge is the evolving nature of malware, which requires continuous updating of the model to adapt to new threats. This can be addressed through incremental learning techniques, where the model is periodically retrained with new data to maintain its effectiveness. Another challenge is the imbalance in datasets, as benign samples often outnumber malicious ones. Techniques such as oversampling, undersampling, and synthetic data generation can be employed to mitigate the impact of class imbalance and improve model performance. The implementation of supervised learning models in real-world scenarios also necessitates considerations for scalability and deployment. Cloud-based platforms such as Amazon Web Services and Google Cloud Platform offer scalable infrastructure for training and deploying machine learning models, enabling professionals to handle large datasets and computationally intensive tasks. These platforms provide integrated machine learning services, such as AWS SageMaker and GCP AI Platform, which streamline the process of building, training, and deploying models, thereby enhancing operational efficiency. In conclusion, supervised learning is a powerful approach for malware classification, offering significant potential for enhancing cybersecurity measures. By leveraging labeled datasets, selecting appropriate features, and utilizing suitable algorithms, professionals can develop models with high accuracy and reliability. Tools and frameworks such as scikit-learn, TensorFlow, and PyTorch facilitate the implementation of these models, while cloud-based platforms provide the necessary infrastructure for scalability and deployment. Despite challenges such as evolving threats and class imbalance, continuous advancements in machine learning techniques and technologies offer promising solutions. By staying abreast of these developments and adopting best practices, cybersecurity professionals can effectively harness supervised learning to safeguard information systems against malware threats.